Welcome to Hot Chips 2024. Keynote 2, The Journey to Life with AI Pervasiveness.
It's my honor, and actually the Hot Chips community honor, to introduce Victor Peng, AMD President. Victor leads AMD's AI-focused business unit and engineering teams, along with the AMD embedded business, formerly Xilinx. Prior to AMD, Victor served as Xilinx CEO for 4 years, culminating in the integration of Xilinx into AMD. Prior to his CEO role, Victor led all of Xilinx R&D, where he laid the foundation of all AI investments at Xilinx, like the AI engine, which is now in the NPU inside of the AMD Ryzen devices. He initiated and drove the Xilinx chiplet strategy, where Xilinx pioneered 2.5D leading technologies like TSMC CoWoS. And of course, he led the Vertex and Zynq products, which made Xilinx the #1 FPGA vendor. Prior to Xilinx, Victor was a CVP at AMD in charge of GPU silicon engineering. And before that, he held multiple engineering roles at silicon stalwarts such as MIPS, SGI, and DEC. And actually, if you go back far enough, nearly 40 years, you can even find him as first author on an ISSCC paper from DEC describing microarchitecture trade-offs of floating point units in MOS. Truly an engineer at heart, with a passion for engineering that has guided his illustrious career. Victor is also now retiring from AMD to the next phase, where he has been appointed to the NSTC steering committee as the only private sector representative, where he will be representing the semiconductor community. So basically all of us here, an important person to know. So let's please welcome the speaker.
Thanks, Ian. Thanks, everyone. It's great to be here. Yeah, I'm going to talk a little differently about really the big picture as opposed to any specific product or technology. I think most everybody here would agree that AI really is going to change, every facet of our daily life, the daily lives of people around the planet, in fact. And this is a chip conference, and my own view. You heard that I'm retiring after over 40 years. Is that there's really quite an entanglement between semiconductors and AI, right? And that actually goes back maybe longer than people think. And certainly going forward, everybody's well aware of how closely coupled. Ongoing delivering performance and capability in silicon is going to help drive, or if we can't keep over the curve, throttle AI progress. So I'm going to first talk very briefly about some of the challenges, and then I'm going to talk about what we're doing at AMD. And when I say pervasive AI, of course, most of what's happening today, the sharp end of the spear, if you will, is in the data center. But we participate also on endpoints, computing endpoints like Ryzen PCs, notebooks, but also in the embedded space. So really, when I say pervasive, I mean when AI is really deployed in mass across all of those things, right? So and if you'll indulge me, as I said, there's a lot of coupling between AI and silicon. I'm not going to go all the way back to the whole AI winter business, but obviously I think back in the all the way back to from the 60s through the 80s, things started evolving to what we're focused on today, neural networks. On the chip side, my first project was a CPU. And in fact, it was a VAX chipset, which I think many of you may not even be aware of what that was. But for those who go back that far, you know what a VAX is. And I thought that was pretty cutting edge. And this was the equivalent of 3,000 nanometer NMOS technology, right? So just to give you an idea, in my journey, I've seen many orders of magnitude in density improvement, many orders of magnitude in performance, and of course, complexity. And later I had the opportunity to work on alphas, so, at the beginning you're talking about CISC architectures, now you're talking about RISC architectures. But I actually, when I was looking back, I also found papers in the early 90s, and I'm not suggesting this is the earliest incarnation, but there are 3 papers on neural networks. Two that were more digital and one that was an analog neural network back in the ICC in 1991. So, really, again, this view that there's progress in both semiconductors and computing as well as in AI. Fast forward to much more modern times, of course, from the AI perspective, the big breakthrough with AlexNet and the data set ImageNet being critical to that. Then transformers fairly soon after that. Now, I put the ChatGPT moment on there, even though in one sense it's not consistent because it's not really a big technical breakthrough. But this is where I think it's important where that's when I think AI in general, Gen AI in particular, really came into the consciousness of everybody around the world. Like literally, I recall after just a few months after that was released and it was getting buzz, like my adult children were asking questions about it. More senior people were asking questions about it. So I think that's really important when you're thinking about what's the progress of things becoming pervasive, because the human interaction and adoption is really critical. Then, of course, continue progress on frontier large language models, but also other types of things like agentic AI. Of course, everything tends to be multimodal these days. There's a lot of effort on that, mixture of experts and so on. So the innovation, if anything, is really continuing to increase in terms of AI. Now, on the bottom, again, this is, okay, it is sort of a conceit on, leveraging some chips that I was involved with. But I think there is a point here is also like, the other point is, when I started in the career, like CPUs did all the heavy lifting on compute. That was it, right? That's what did it. And it wasn't that long ago, this whole notion of heterogeneous computing and accelerated computing was really a new concept. Of course, now with GPUs and AI, everybody takes it for granted, but it really wasn't that long ago that really it was still CPUs, maybe with, okay, we integrated floating point accelerators and so forth, but CPUs did all the heavy lifting, and I think that's changed. So some of the products here is when we integrated the Zynq, the first generation Zynq is when we integrated, multi-core ARM SoC, a full SoC with local memory and peripherals and so forth together with programmable logic. And then earlier this morning, if you caught it, there was, the Versal Edge product, which is the next generation, much more complex SoC, AI acceleration with the programmable fabric and many other accelerated hard blocks. So this notion of heterogeneity is clearly the future of computing as well, right? And then, of course, the last product there is the MI300X. And, I'll spend quite a bit more time. There's a paper on that as well. But, again, the leading edge of this journey to pervasive AI is certainly starting in the data center. Okay, and again, zooming out even again in the big picture, like I said, the tip of the spear is in the data center. And so there's a lot of focus on building enormous infrastructure for, training these frontier large language models, but everything else. And then, of course, serving inference is also going to grow. That's still, in the early stages of growth. Endpoints, when I talk about endpoints here, I do mean more traditional computing endpoints. So, your personal devices, so notebooks and desktops and other personal devices. We've probably, that has started. We've probably only had about a couple of generations of AI PCs, and the types of models that are running on that are still pretty limited, but it's growing exponentially, and that will continue over time. By the way, I guess I should have said, it's a dead giveaway when there's no, y-axis on exactly what this is. But you could look at this as, unit volume growth or the growth or just absolute units. And certainly, this is not quantitative. It's just trying to give qualitative idea of, this notion of multiple cycles to really get to ubiquity on AI is just, it's going in a pretty big fashion in the data center, but just starting at endpoints. And I would say, yes, there are a few areas embedded like automotive, robotics certainly, and a few other areas where there's been AI for some time, but it really hasn't inflected, and that's really in front of us. So whether you look at each individual one or you put it together and say you're going to have 3 successions of cycles, it really is a super cycle that I believe really will last for decades. And as much investment and value is starting to be created today, we're really in the early phases. So speaking about investment, recently, I'd say in the past few months, there's been a lot of discussion about this big question of like, wow, the investment level, particularly for these supercomputer infra for training the frontier models, is increasing at a tremendous rate, and on an absolute basis, a huge amount. I heard there was some questions earlier and yesterday perhaps around this. And the reason why I'm just bringing this up, and I'm not really going to deal with this macro issue so much, is just like when you look at the challenges in front of truly having pervasive AI, it's not purely technical. It's not, there are human dynamics. I was saying, in terms of the ChatGPT moment being, a positive thing in terms of that, or mostly positive, but also, just business investments and things of that nature. So I'm not going to talk about this too much more, but certainly that's an area that if we, the people in the industry that are generating technology to help create that value, right, stay ahead of the investment level, then it all works. It's a beautiful cycle. And on the other hand, if there's issues, there'll probably be some, let's say, different rate and pace in terms of how this thing gets deployed. And, to that point, it's always nice to draw a straight line or up and to the right kind of line. The reality is always never like that, and these dashes and dots are really just meant to say that really there's going to be bursts, there's going to be periods where maybe the progress is either in innovation, probably more so deployment than innovation, may have different rates, right? But at the end of the day, I do think, and I think most of you I'm sure would agree, that the big picture perspective is going to happen. Predicting timing is always difficult, but what's most important to keep in mind is, this transformation and those super cycles, right? So, in addition to that whole issue around the, patience of capital for investments, there are other challenges that are more macro that I'm not going to do in this talk, but it's probably still worth mentioning. A lot of people talk about the data wall. People have scarfed up the internet, but also there's also issues around tainting of the internet since AI is now producing a lot of content on the internet. So data sets are super important, and also as you get to a certain level of accuracy or intelligence, however you want to think about it, to get further, you really start needing expert and really clean data, and so that's really critical. Then other things like safety, reliability, privacy, and so forth, right? Now, what I will spend more time talking about is really the technology challenges, right? And certainly there, first and foremost, really power, right? And if you look at it at the macro level, for those huge deployments, we're talking about not even finding enough power sources and being concerned about the grids and the distribution. So I think everybody is well aware that the hyperscalers in many different places that are buying up capacity for power, locating things near power sources, looking at grids, and there are many projects around the world to actually create new power sources specifically to build AI infrastructure, right? What that does inform us in the semiconductor industry, of course, is a key figure of merit that you have to worry about is not just performance, but performance and energy efficiency or power efficiency. So, and also, of course, there is a cost element, right? So the way I would look at it is the key figure of merit, and in fact, I would say no matter where you are, whether you're playing in the data center, on endpoints and the embedded edge, you really need to look at performance per watt dollar. Now, watts and thermal tends to correlate oftentimes with performance as well, but in any event, that's sort of the key figure of merit. The other aspect here is, where a lot of focus is on data center. Again, when you start getting into the embedded world especially, but even, on endpoints, the requirements or the key objective functions really do get weighted differently. And that presents a lot of challenges, right? Because, for instance, the easy one to pick on is latency, right? Like a lot of, if you're training big models or even if you're serving up in the cloud, a lot of those applications have some degree of latency, requirements, but they're not too much if it's just about, holding your attention for a recommendation or something like that. But on the other hand, if you got the Versal edge product, and that's being in automotive, it's a lot of different kind of latency requirements if you're doing, automotive control and you're driving at 100 to 200 kilometers per hour, depending upon where you are. And so that's just one example of that. And so I think a big challenge in truly getting AI to be pervasive is going to be, how do you cover that very diverse range of requirements? Okay, so this one I think everybody's seen different versions of. The key thing is, as it turns out, this has held up quite well for some generations of these large frontier language models, that if you throw more computes, you grow the size of the model, you will get better performance, accuracy, levels of intelligence, however you want to think about this. And so we've moved fairly quickly from orders of magnitude. The y-axis here is hundreds of megawatts to hundreds of gigawatt hours in order to train these things. And again, it's generating that whole rush to power sources and grids and so forth. I think a lot of people have looked at this thing, and I think I've seen analysis. Epoch AI did something interesting fairly recently, and they certainly look at it and say, seems like it's possible to sort of get to the end of this decade, but if exponentials continue to grow, it gets kind of interesting what your belief is about beyond that. But it certainly, this again underscores the importance of the performance per watt, because obviously for whatever power budget you think you're limited at, if you get higher performance, you could either train larger models and get to intelligence quicker, or you can serve it more cost effectively, and also when you get to inference. Okay, so again, while I'll talk a lot about data center, you really have to look at each of data center, endpoints, and embedded. And there's a breakdown of where the power is really going. And if you look at the data center, most of it, as one would expect, is in the AI accelerators. Mostly that's GPUs. There's still the CPU head nodes. Quite a lot of it is in the network, and we will talk about that. And I think there are a lot of papers about talking about how to optimize networks for exactly that reason, because you get throttle performance, but also a lot of power is being burned in the network, right? And then the other is sort of all the other elements of the data center, as well as distribution and other kinds of overhead. Now the endpoint one, that kind of comes from looking at some of the the notebooks and things that we have. So these are really from AMD kind of products. I would caution that here it doesn't look like there's as much going to the compute, and and of course we know that for notebooks, like just driving the screen is a lot of power, and there's a lot of other things. However, what I would also say is that I think that because we're in the very early stages, the amount of AI, the types of models, how many are running concurrently and so forth, it's just kind of early. And I know that what's happening in the very near future is that that's going to grow also exponentially. So I think the mixture of the breakdown in power there will change over time. And then in embedded, now embedded is so broad, right? Like this, this is just one instance. It is sort of based on a mid-range embedded product that we have at AMD. So it's not it's not totally constructed, and of course there you look at it's roughly 50-50. A lot of that is because there are all kinds of different interfaces, IOs and memory associated with that, but that can certainly vary quite a lot. The key thing is if you look at it though, there are different orders of magnitude, right, when you go to each of these steps, and these are kind of like at the I guess what I would say, the data center is at the data center scale level, right? Certainly for the endpoint, now you're talking about the device, so you don't have things like scale out or scale up networks, but the system is largely the SoC, so you have a fabric there, and you have heterogeneous computing, which I'll talk about. And embedded devices, it could be quite heterogeneous, so there still a lot of complexity, but just different order of magnitude in performance, power, cost, and form factor, right? So and then, hitting across that notion that because of the breadth of applications and use cases of different models and different requirements, while there is overlap, when you look at it, there are some significant differences. And I already kind of prefetched the notion about latency being a very big issue. That's much more of an issue for embedded AI in most cases than it would be for even things at the endpoint and certainly in the data center. Now, the endpoint is someplace in between because there's a lot of, obviously it's your device, so there's a lot of human, machine interaction at that point, but the deadlines aren't necessarily quite as bad as, like I said, in, say, robotics or, automotive or avionics, for instance, okay? So that's the challenges section. So now, I talk about what we're doing at AMD to find solutions to these challenges. And first, really focus on the energy efficiency performance piece. Then I'll cover, how we address the diversity of the requirements. So, AMD's been really focused on not only performance, but performance and efficiency for quite many generations of products, right? Here, we're just looking at, several generations of EPYC server CPUs. And if you kind of normalize to 3 generations ago, the Naples with 32 cores, then you look at Milan, Genoa, the core count's increasing, and the performance per watt is also, doubling from from Naples to Milan, and then, increasing substantially 50% or so in Genoa. And then Bergamo is the more recent one where the focus there was just, again, having a tremendous amount of core density. So, over that time, factors of improvement. And it's not just core count, right? You have to really, and this is a point that I'm going to make shortly, is that you really have to optimize the entire hardware stack. And of course, the hardware stack has to be, co-optimized with the software, but I'll focus a little bit more on hardware since this is a chip conference. And so, we've really been focused on this for quite some time. And we take that same maniacal focus, not just for the data center, but across the board and all of these things. And as I alluded to, you really have to do it at every level, and that's one of the things, particularly about AI. And if we think about the data center, that's so mind-boggling complex, as well as so incredibly interesting if you love solving hard problems, because you have to optimize things starting from base technology, right? Through architecture, microarchitecture, implementation, to the system level, and indeed at the entire data center level, right? So I'm going to walk a little bit through all of those, starting from the base technology and moving up. Okay, everybody knows that it used to be, back in the good old days, Moore's law and Dennard scaling worked. That kind of stopped back in around 90 nanometer, quite some time ago. And since then, we've been changing materials, we've been changing transistor architectures. So even with going to FinFETs and gate-all-around, what you see is a 2-plot. There's density, and by the way, this is mainly logic density, so it's looking at how logic per millimeter squared is shrinking. If you take a general case of around a 250 millimeter squared device. On the power curve, what we're showing is ISO performance. So for constant performance, what's been the trend of power efficiency? The density you see rolling off, right? Despite all these tricks, and for many, many years, right? You didn't change the transistor architecture. Now, the transistor architecture only lasts like 3 nodes, and then we're about to go to gate-all-around, right? I think the other thing is on the power, and here we're looking at power ISO performance. You could deduce performance, so everybody thinks about PPA by just changing that. But basically, you see that looks like it's kind of keeping up. But remember, this includes everything, including voltage scaling, right? And that's getting more challenging, right? Scaling that further, especially when you still have to hit certain performance, right? So that's sort of kept up. But the other thing, too, is that the timing of when the nodes come out has started to slow down. I think everybody's kind of talked about this. So, why are there a lot of people in the industry still say, oh, Moore's law is still alive and well? Well, that's because if you broaden the scope of, I guess I'll talk about that in a minute. But before I get to that, PPA, just to finish that, the A is meant to be the surrogate for cost. But if you kind of look at it, yes, the A is, density is still scaling, it's rolling off a little bit, it's still scaling, but the cost is going up, right? And this is cost as in wafer pricing, yield, all the things, defect densities, all these things that are happening. So really PPA is the underpinning for why every consumer on the planet thinks it's like electronics always gets faster, better, cheaper every year, right? So, I think thanks to the ingenuity and the innovation of the industry, we've managed to keep that, perspective alive for a while. But I think basically what this is saying is going to be very, very difficult. We have to, dig even deeper in terms of our innovation. Because, again, it used to be mode to node, you get all 3 PPA improves. You can get one of them, maybe get 1.5. You really have to innovate to get the other 2 along. So what I was going to say is, why do some people still say Moore's law alive and well? Well, if you increase the scope of Moore's law to include non-monolithic integration and advanced packaging, then okay, you can integrate more in a package, right? But of course, the complexity of that is quite a bit higher. But it does work on multiple levels, right? I mean, fundamentally, what you're helping to do now is you're improving compute density, and also you're improving locality, right? So if you keep not only logic close together if they have to interact, but if you're keeping memory and logic close together, that's a win both in terms of performance as well as power, because obviously you have high bandwidth, because you have a lot more bandwidth staying within a package, certainly within a die. You have also lower latency, and then you're not burning power, shipping bits across, a lot of capacitance out either on the board or through the system across the whole data center. So the plot just shows, this kind of flipped. A lot of people show joules per bit of bandwidth. This is flipped the other way around, so higher is better. And basically, of course, everybody knows that if you go off package, it really hurts. Even with optical, the interesting thing, staying on in package is better than optical interconnect. And then certainly if you do 2.5D integration, so of course everybody's doing that gangbusters with the most advanced chips. We've been doing that certainly with the MI300 and EPIC. But then also if you add on to 3D stacking, so active on active chip stacking, now you get an even bigger boost, and that's obviously because you're not limited now by the bisectional bandwidth of a 2D structure. You get all the interconnect going straight up vertical. So that's really compelling, and indeed we have done that with the Milan X and with the on our EPIC CPU and the MI300X. We have 3D cache stacked actively, 3D on it, as well as 2.5D with both chiplets as well as HBM. Okay, so moving from base technology and how that interacts. By the way, that obviously interacts with your architecture and microarchitecture because you have to partition things differently and so on and so forth. But if I go, also take another track and say, well, quantization clearly gives you significant performance improvements at actually even, more efficient power. So there's been a lot done here. It started in the early days with AI, FP32, got into half precision. We're moving, and she's moving to 8-bit, but there's obviously even lower precisions and mixed precisions that's really helping with this power efficiency. So really, this is a key lever. We're an active member of the OCP MXFP working group. We just recently announced that we will be supporting FP8 as well as FP6 and 4 in our future MI roadmap, the MI350. And we continue to do more innovations. Our research team, if you look at when you start getting to the limits of, quantization and activations and weights, another area that our team has recognized is that you can start looking at the accumulators themselves, right? And if you optimize the accumulators, understand that you're using these mixed precisions, there's quite a lot of improvement that could be had there. And there's other things that we're doing, and the teams actually open source some of these things in the library. So I think there's a footnote at the bottom here, so if you want to look at that, if you're interested in more details. But there's, certainly, I'm not mentioning sparsity. There's other things at that level that both interacts with the architecture, microarchitecture, and of course the algorithms and the models. Okay, another angle on this architecture, and this tends to, again, be used in a lot of, and indeed we do that with the AI engine, also called XDNA, where I talked about, embedded applications where latency is important, and also you're working with an even more stringent power and cost budget. So data flow architectures, and in general, you can just think about, so of course, you're now specializing the architecture even further, where you might be representing, less of a regular kind of network. You might be also, combining the optimizations, the quantization with different layers. You might be mapping quite literally, the structure of the network to the hardware, and we could do this with things like FPGAs. But even before that, there's significant gains to be had when you're just, you're not moving data to and from registers or memory or caches, and data is just flowing, layer by layer or however that's constructed. The bottom thing is showing, again, from a research perspective, where our R&D group literally took and optimized, layer by layer, an executable form of that network, and saw a 4,500x improvement. So I'm sure there might be some reference there as well. Okay, so those are things at the base layer, at the architecture level. I started out talking about how there's entanglement between semiconductors and computing and AI, and heterogeneity in general is one of them. Well, if you look at, I mentioned again, if you saw the Versal AI Edge product, that's truly a very heterogeneous, product for automotive and other applications. The same thing goes for our Ryzen for desktop and notebooks. We have, Zen cores, up to 12 of those, latest generation cores. We have RDNA 3.5 architecture GPUs, and then we have this, by the way, is which we just recently announced, the Strix Point, the third generation of our AI PC product line. And we have a 50 top NPU, that's the AIE XDNA. So, clearly you get a lot of efficiency here by mapping the proper workloads onto the most optimized architecture for that, right? So you can imagine you're running, some gems on the NPU. Well, the CPU is doing control, or maybe doing some vector database, and then you could also be doing, graphics, or whether it's graphics or diffusion kind of architectures all in parallel and concurrently. So again, it's specialization at a SoC architecture level, if you will, or heterogeneity at that level. Okay, popping back to data center, I talked about data movement and talked about that in, sort of coming at it from off package or on package. But then certainly, if you go further than that with large frontier models, you got to shard those models across the entire data center. Again, just to sort of, if you normalize, you stay on chip, and let's say you're just moving data from a register file to your data path, that's one. Then, by the time you're moving data across a scale-out network, it's like 5,000x more power to do that data movement. And of course, scale-up interconnect is someplace in between, but still 3 orders of magnitude greater than staying, on die, and several orders of just staying within package. So, clearly, the scale-up as well as the scale-out network is super critical. We feel this is so important, and since there's different players, when you get to the data center level, our approach is we've just recently been working with the industry to build this standard, the ultra accelerated link standard for scale up, and then also we're part of the ultra Ethernet in terms of scale out, and really looking at a version of ultra Ethernet that could be more focused on kind of like the congestion control and a more streamlined protocol for data movement and packet size, the things that are more akin for ML applications. I think there was already a talk on the MI300X, so I won't belabor this. Just very quickly, this what we're thinking about in terms of the Infinity Fabric, and we're donating the SGMI technology and our learnings from that to that consortium, and just it basically is still something that enables very high cross-sectional bandwidth. It provides all coherent memory, and then of course all the DMA that you need. Okay, so that was the first area, and all the things we're doing in the different areas for performance and energy efficiency. So now I'll talk a little bit about, how do we deal with the fact that, for all these different markets and use cases, the requirements are pretty diverse. And look, it starts with a pretty basic thing, right? Like we have a very broad set of product portfolios, server class CPUs, client CPUs, GPUs, adaptive SoCs, which is SoCs integrated together with FPGA fabric and other kind of hardened accelerators, as well as pure FPGAs. We also have which is not shown here, but network technology with DPUs. So from an architecture perspective, we really can target like which are the architectures that are best suited for the requirements, right? So as opposed to taking more of a one-size-fits-all, like if we're mainly whatever an X kind of processor kind of company, we don't have to do that, right? We could really target things that from first principles are most performant as well as power efficient, and then we can optimize further for those exact workloads, right? And that's exactly what we're doing. And and I already talked about chiplets. The other thing is that AMD independently prior to the combination of Xilinx and AMD, was doing chiplets, a leader in that area. We at Xilinx, we didn't call them chiplets, but we actually had 2.5D integration since the 28 nanometer generation. We were, for the longest time, the one and only production customer of TSMC with CoWoS. And then in both cases, with this leadership, now with 3D capability on top of the 2.5D, that certainly enables us to target, different performance and power and cost points. It does enforce a certain modularity in architecture as well. So it also helps you also bring, customize things and bring things to market, quickly. So, I think this technology not only helps with that performance per watt thing that we talked about, but it also helps in terms of how you optimize for different, requirements. And I've mentioned this a few times, but it really is worth emphasizing quite a bit, which is all those things that you put in the hardware, right? And even if it's at the system level, if you don't optimize together with that the algorithms, the models, and the software stack, then you really don't see the benefit of that. Indeed, actually, you could see degradations. We've all aware of those sorts of things. So I think it's really important to do the co-design, and that's why AMD partners very closely with all their customers. It also works with industry partners and so forth, and really optimize each one of these aspects. The system software, the basic models and algorithms themselves, all the hardware, and whether that's at the chip node level or data center level. For the data center, you have to work at that entire level. That's super critical, and that's in fact what we do. And following on that kind of line of thinking, you've heard me in other forums, and I'm sure you've heard people from AMD talk about, that we have a more open strategy. We really believe that while we're bringing tremendous innovation and value to the marketplace and our customers, with all that technology I mentioned, that we're best serving our customers as well as the industry as a whole to really work with the ecosystem and work with partners, because the innovation, the rate of innovation is just phenomenal, right? I think even in this conference you could see that, and I think the breadth of the innovation is also pretty phenomenal, and that's something that maybe not everybody necessarily appreciates, because again, there's fewer people focused on the embedded space than maybe what you hear about the data center. But it's the rate and pace as well as the breadth is enormous. And I think we all know that the open source communities and a lot of these open consortia really can give you that speed like no other in terms of innovation, but also the breadth. So we partnered with Hugging Face quite some time ago, 700,000 models and growing across a range of different sizes and capability. All runs on AMD out of the box. We're closely working with the Torch Foundation, PyTorch, also other big frameworks, JAX, TensorFlow, and so forth. OpenAI Triton is becoming more and more of an important thing in terms of kernel generation and so forth, and we're ensuring that that works and on every release as well. And then our compiler stack is heavily based on VLM and so on. So we're working very closely with the ecosystem, the full stack, and that helps. We bring value to the ecosystems or our powerful platforms, and then we get value from all the innovation and the breadth of what they do to offer the broader industry and our customers, of course. So this is really this aspect is really key to our strategy. So and hopefully this puts us in context when you think about what it's going to take to really make AI ubiquitous. So, I started out by saying, it's in early days, right? So, while it is early days, I don't want to make it sound like not that much is happening, especially with this whole debate about when is the revenue going to show up versus the investment level. I mean, we've got production deployments, we've got many active engagements, in cloud, on the edge, embedded edge, endpoints and so forth, with a whole litany of different industry leaders, and this continues to grow, right? So the message is, yes, it's still early days, but there really is a tremendous amount of innovation and activity happening. So I have no doubt, again, calling the exact timing is difficult. Calling whether it's going to happen, at least from my perspective, is not. It's going to happen. So what I'll do next is just show just a few examples. There's a couple of demos, a couple of things just to walk you through in each of those areas, right, where people are utilizing AMD platforms in the cloud or using some of our endpoint devices in the embedded space. So first, in terms of model development, I think everybody knows, Llama, and it kind of flows well since I just talked about the open source. They truly have just released, in the open source, very powerful models, and harkening back to the fact that I said, we've done, I think, a great job with the MI300X in terms of, the compute density, also integration with high bandwidth memory, which is a win for performance as well as a win for power. And you can see with this latest generation, the 400 billion parameter model fits well within one 8 GPU MI300 node. So very powerful. And given that it's open source, there's a lot of democratization of giving people capability. They may start with this frontier model, but then of course they'll specialize it, they'll fine tune it, add RAG or whatever it is. And basically, again, I think you could see where this interaction of open source and some of the optimizations we have done for data center GPU is paying off. Now, this is a bit of a demo that's run from 310 AI, and what they do is a text to molecular generation. In this case, you can see you're writing text and they're creating proteins. And the notion here is they're trying to see are there proteins that can help fight cancer. But basically, this is not only for bioscience, it also can be used for chemical development and other things. So this actually, I believe, is running on EPYC processors as well as Instinct GPUs. I think this is just still 250, which is the previous generation. So when they get on the MI300X, that will really turbocharge their capability here. So pretty amazing, application. Again, just one of several here. And okay, so this next one is stable diffusion, and again text to image, and of course there's also text to video. This certainly of course runs in our data center GPUs, but it also runs in our consumer GPUs. So again, this is an application. Certainly, I think the way gaming is done, you're already having it for super resolution, but just in general, you can see how over time, AI is going to be revolutionizing gaming, and not just the imaging, but the characters and so on and so forth. So here's an embedded one. This is kind of interesting. It's agriculture, but it's fish agriculture, if you will. And this is image recognition with an image recognizer on an FPGA module, and it's looking at this fish, and looking for fish that are not healthy, and so to prevent contaminating a significant part of the fish crop, it automatically then steers fish that don't look healthy in a different way. And so again, this is actually on a fairly, mid-ish range, not a very powerful FPGA. So of course, when we accelerate that, you could imagine you could have much more interesting things. The other thing, I made a big thing about how latency is a big thing for the embedded space. And you kind of go like, well, those fish aren't moving terribly fast. That doesn't seem so impressive, right? So the next one, FPGAs are also used in the CERN, collider, particle collider, hadron collider. And this is where it's creating terabits of data in a collision, in microseconds. And there are many, many billions of collisions per second. And basically, it's generating so much data. What you have to do is they're using tens of thousands of FPGA, very specialized, AI to recognize particles that might be of interest, and then storing that, because they cannot possibly store all the data that's being generated by these collisions. And then they could offline, with less latency requirements, process the interesting particles and things that get emitted from these collisions. So here's a case where the real-time, the latency issue is a little bit more stringent, and you can kind of see. And I think you can kind of also see this diversity of the requirements that you need for all these applications. By the way, I think this is many hundreds of 100 meter underground and different environments. So that's the other thing about embedded. You have many different environments that you have to deal with. So that's just kind of a very light sampling of end-to-end AI that AMD is doing. So look, I'm using this metaphor. It's a long journey, and we're in the early stages of it. I know that people have different views of what it leads to. I certainly, I think like most technologists are optimists and think about really all the tremendous things you could do to improve quality of life. and it really is going to be pervasive in our daily lives, not only at work, but at home, where we live, in the infrastructure, all forms of infrastructure, not just IT, communications infrastructure, but infrastructure like cities and streets and even in rural areas. By the way, this image was generated also through Stable Diffusion. It was the only one that was. So the rest was generated by humans. Midjourney in this case. Again, I hope this overview gives you an idea that, across all of this, a really key area to sort of focus on is that effective delivered performance per watt dollar. You have several orders of magnitude difference depending upon where you live. And AMD is delivering those systems, working together closely with our partners, our customers, and the ecosystem, to realize AI pervasiveness from cloud to endpoints. And maybe, I talked a little bit about, for me, and it was Ian mentioned that I was retiring. I will say on a personal note, I never would have dreamed that, when I started out in '82, I like to think of it as kind of a golden age of computing and semiconductors. I mean, the EDA industry didn't even start. There was no fabless model. We were talking about CISC versus RISC and mainframe, so, the PC thing was just starting. But I never thought that at the end of my career, after these orders of magnitude, that it would also feel like the new golden age of computing and for semiconductors as well. So it's a really super exciting time, and certainly grateful for my part of the journey here, and thank you for listening. So.
Excellent. Excellent. Thank you for that wonderful keynote, Victor. So before we take some questions from Slack and the audience, I have one question for you. You've worked in this space for a long time. You've seen different booms and busts and different disruptive technologies like mobile computing, PC computing, the internet, and now we're on AI. And I think a lot of folks in this room believe the AI hype, but maybe not everyone. So where would you put AI in the spectrum of technologies? Do you think this is the biggest one you've seen? Do you think it's similar to other trends that have happened in the past? What are your thoughts there?
Yeah, first of all, what I would say is that there's certainly hype, but it's also real, right? So we don't want to conflate the fact that there's a lot of hype means therefore it's not real. And certainly, again, as I said, in terms of finances, are there going to be business models that don't work out? Are there going to be some people lose money? Yes, but I personally believe that this is absolutely real, and I also believe that the internet's probably the closest thing, because the internet really has changed all of our lives, and it really has created whole businesses and changed a lot of things. I actually think in the long arc of time, AI will be even bigger. And by the way, and part of the reason why you could see this rate and pace of AI is because we have an internet. It's because we have an open source collaboration model, right? We didn't have those things for some of these other transformations, like going all the way back to when PCs first came around, right? So I think there's definitely accelerators that come together on that.
Great. All right, thank you. Let's go to Slack. First question.
Thanks for the fascinating talk. This question is from Cliff Young, Google. It feels that we as architects have been chasing the algorithms of the ML revolution. What they find important, we eventually make fast and efficient. Are there things we could do to accelerate the rate of discovery of new machine learning algorithms beyond performance and efficiency? For example, the original GPU revolution was not aiming specifically for machine learning and helped many different fields.
Yeah, no, that's a great question, and I also remember that. I remember when CUDA came out. I was actually at ATI when we came up with CTM. Like, okay, clearly that didn't really win over. But one thing that is happening that I think everybody that in semiconductors knows is this whole big other effort of shifting left, right? And trying to accelerate the design cycles, because that's the other thing about one of the downsides of these complex technologies, and also really complex integration technology like 2.5D and 3D is it's creating time to getting first silicon out much longer. So there's left shifting, and I think that's not just left shifting from a silicon design perspective. I mean, this goes back to you have to invest heavily, and we are at AMD, in performance modeling all the way up to the model level, right? And you have to, for the data center, you have to model the network. I mean, so a lot of that is going to be really important. I think this is such a rich area too. I think, I mentioned it, but I said I'm not going to talk about the data wall. I think there's also a lot of things that has to happen, innovations around data. And people are working on synthetic data. People are working on other things, simulation. So I think those are things, you need to solve the data. You need to speed up, the architectural exploration, and you need to shorten the time it takes to develop and manufacture these super complex products.
So actually, just to build on that question a little bit, you spoke quite eloquently about the desire and need for delivering on this energy efficiency, and often that comes a bit at the cost of flexibility, which might be used to explore some of these new things. So how do we as architects walk that tightrope, I guess, in terms of efficiency, but still enabling kind of the next level of innovation?
Yeah, that is a really, this whole thing about, I mentioned, you get factors of improvement if you specialize, but then, you better be right about what you specialize. And it's difficult, right? And we all know to do an ASIC, you need stable specs, right? So it's difficult when things are so dynamic right now. So what I would say is that, look, I've been wrong before, I'll be wrong again, but I feel it feels a little early for people to do special hardwired kind of AI things, because by doing that, you're also then limiting experimentation on that very platform, right? So there does need to be some specialization, but you have to do it very thoughtfully. This is something that's going to be really powerful, like the data types. I mean, it's pretty clear. The other area people are exploring is sparsity, but you can't, if you go all the way and just target one specific network, I'm not sure, it'll do that great, but then somebody will just, come up with a better network, and then you're just SOL, right? So.
Okay, great. Let's take some questions from the audience. And just a reminder, this is a technical conference, so not an investor relations conference.
Despite the fact that I mentioned the dreaded investment value creation thing.
Sarah Bivani, it's good to see you, Victor. At one point, we worked in HLO2 together every day.
Oh, my goodness. Great to see you.
Good to see you. I still have your PCI book, by the way. As technologists, as computer architects, we're always optimizing, PPA, performance, and costs and so forth. But and then in terms of pervasive AI, we've seen some applications of AI that are very pervasive. They're picking out targets by automated drones and doing bad things. So how do we, as technologists, do we have these frameworks for ethics and for regulation? So what are your thoughts about who should do regulations and how should we as technologists be involved?
Yeah, wow, there are whole conferences just on this topic, right? And I kind of mentioned and said it's outside the scope, but I will say part of my responsibility, I also help as executive sponsor, help bring up our Responsible AI Council. And, we are actively working on that. I do think it's not easy, but I do think that, what the industry has done together collectively has not been easy. So I think it does drive us to be even that much more thoughtful. I like to use the term not be smart, but also be wise. I don't think it means it has to slow down innovation, right? I don't buy the dichotomy of either stop everything, because you're a doomer, or it's full speed ahead and AI would be so, brilliant that it will never do anything harmful. I do think in terms of regulation, I mean, that could be a throttle. I think that, the key thing, what I tend to think about is regulate the use cases, not the base technology, right? And Andrew Ng has made a similar point. It's kind of like you don't regulate electricity if it's a general purpose technology. You regulate electricity that's maybe using some whippet system, and things of that nature. I also think that, you have to really be careful about unintended consequences. So the key is, be very thoughtful. I think the other thing that's very bad for industry and progress is if, at the state level, at different nationalities, at different geography, everybody creates different regulations, right? That's clearly, a fiasco from friction and so on and so forth. So it's a challenging problem. I don't think I have the answers, but I do think that it's not a bad thing that we technologists have to also think about societal impact. But you should not take that to mean that I think we should slow down. We need to do a moratorium.
I was thinking around safety, so thank you.
Yes.
Hi, Nathan Brookwood, Insight 64. Excellent talk. Now that you're moving into the world of bureaucracy with NTSC, one, what do you hope to achieve there? And two, how do you think you're going to be able to deal with that, not having direct control over anything the way you have had at Xilinx and AMD?
Okay, I have to admit, didn't expect that question. Look, the folks in government, I mean, first of all, since at Xilinx I was on the board of SIA and I've had to deal with government for a number of years now, I would say that a lot of government has gotten way smarter about semiconductors in general and really coming up to speed on AI. That said, they could certainly still help, whether it's me or someone else from the private sector. So one big mission I have is just help educate, make sure that there's better understanding, really foster communication between the private sector and government. So we can have careful, very maybe thoughtful in some areas regulation when it's needed and not do knee-jerk stuff that aren't thought through. In terms of how I'm going to deal with the maybe less control, we'll see. I guess I really look at it as, you have to figure out how to use a different muscle to influence. That's always the best way to influence internally to a company anyways, is not to exercise your positional power, but, by hopefully the merits of your ideas. But anyway, so we'll see.
Okay, thank you.
Thank you.
Thank you. Jen Lee at Future Way Technologies. Great talk. Thank you so much. I want to follow up on the 4500 energy efficiency improvement on sparse data flow. It appears to me that's for DNN on IPGA. If we change the case to LLM to like GPU ASIC, what would be that number?
Yeah, I will say I don't want to overstate what that was. That was an example of some research we did. If you take to a pretty far extreme specialization, exactly your point, Ian, right, where you're literally implementing layer by layer, you're optimizing what precision works for that layer. You could deal with irregularity and sparsity, right? You can get huge factors like 3 orders of magnitude. I'm not suggesting you could possibly necessarily do it for any kind of model. So maybe there are people in my R&D group that can say what they think, what gains might be there for some degree of specialization for even LLMs, but I'm sure it's not going to be that kind of order of magnitude kind of gain, right?
Okay, thank you.
All right, I think we're out of time. So Victor, I'd like to thank you again for a great keynote, and actually thank you for everything that you've done for the community and the Hot Chips community.
Thank you.
And
Thank you, everyone. Thanks.